Here we present Boyle's law as the first one of the gas laws. Boyle's law formulates the everyday experience related to the compressibility of gases, which is very high compared to the one of liquids. A gas has a high compressibility if a small amount of change in pressure causes for the gas to have a great change in volume at a constant temperature. For example, we can consider a mini syringe pumping air in a balloon. If we compress air in a syringe to a small volume, we can pump this same amount of gas into the balloon. As a result, the gas will expand and inflates the balloon. Historically, Richard Townley and Henry Power were the first researchers in 1661 who tried to establish the barometric formula. They measured the air pressure on different altitudes along a hillside by using a Torricelli-type barometer, and they were able to establish a relationship between the pressure and the density of air. Powell published the results of their measurement in his book with the title Experimental Philosophy. Boyle saw the early draft of the book and have discussions with Townley. In the following year, Robert Boyle and Robert Hooke carried out a series of experiments related to the measurements made by Townley and Power. In the experiments, Boyle confirmed their findings. Hooke built a set of experimental apparatus shown in the figure. One of the devices in the picture is a J-shaped glass tube immersed in water bath, in which air was sealed with different amounts of mercury. Boyle demonstrated with the device that the pressure of the air is inversely proportional to its volume. However, Boyle was not the only one who carried out experiments to find this kind of relationships between the physical properties of the air. In 1679, Edmé Mariotte discovered Boyle's results as well. He also showed that the volume of a gas changes with its temperature, which is another important result related to another gas law. Now we present Boyle's experiment in which he determined the relationship between the pressure and the volume of a gas at a constant temperature. We will use an apparatus somewhat different from Hooke's J-shaped glass tube, but the principle of the measurement is the same. Let us connect two glass tubes with a rubber tube and form a U-shaped tube. The glass tube forming the left arm of the U-shaped tube has a tap which is left open. We pour some mercury into tube so that the upper surfaces of the mercury column are located at the levels A and A'. By closing the tap, we close the air over the mercury column in the left arm of the tube. The air enclosed in the space between the tap and the mercury column with the height A is indicated by the yellow color. Let us denote the volume of the enclosed space by V1, and the pressure of the air in this volume by P1, which is still the atmospheric pressure. That is, P1 is equal to 1 atmosphere or 76 centimeters of mercury. By elevating the right arm of the U-shaped tube, the mercury columns have the heights B and B' in the glass tubes. We lift the right arm in such a position, so that we could decrease the volume of the air enclosed in the space between the tap and the mercury to 3/4 of its original value. That is, the reduced volume, denoted with V2 is equal to 3/4 times V1. The difference between the heights B' and B of the mercury columns determines the pressure of the air closed in the reduced volume. The measured difference is about 25 centimeters. Then the pressure in the closed volume, denoted with P2 is given by the sum of 76 and 25 centimeters of the mercury levels. The ratio of P1 to P2 is equal to 76 divided by 76 plus 25, which gives 4/3. Therefore, P2 is equal to 4/3 of the atmospheric pressure P1. As a result, the product of the pressure and the volume of the air remains constant, that is P1 times V1 is equal to P2 times V2. Now we lower the right arm of the U-shaped tube, so that the volume of the closed air column could increase to 5/4 of its initial volume. By denoting this increased volume with V3, we can see that V3 is equal to 5/4 times V1. The mercury columns have the heights of C and C' respectively, and the difference measured between the levels C' and C is 15 centimeters. The pressure of the air in the increased volume is denoted by P3. Then the ratio of P1 to P3 is given by 76 divided by 76 minus 15, which is equal to approximately 5/4. As a result, the pressure P3 is equal to 4/5 times the pressure P1. That is, P1 times V1 is equal to P3 times V3. We have demonstrated that the product of the pressure and the volume of the air enclosed in the left arm of the U-shaped tube remains constant, regardless of its volume. Therefore, P1 times V1 is equal to P2 times V2, and also to P3 times V3. Then the experiment shows that the product of the pressure and the volume of a given amount of air is the same for an arbitrary volume or an arbitrary pressure. More accurate experiments demonstrate the same result with a gas under given circumstances. For example, we obtain this result for air with a pressure under 300 atmospheres at room temperature in a relatively big volume. Then Boyle's law, discovered in 1662, states that, at a constant temperature, the product of the pressure and the volume of a gas with a given mass is constant. That is, P times V is equal to a constant. This gas law can be rephrased in another form too. Since the density is equal to the ratio of the mass to the volume, and the mass is constant, the volume of a gas can be expressed in the terms of its density. Therefore, the gas law also states that the ratio of the pressure of a gas to its density is constant. The constant in the right-hand side of the gas law depends on the properties of the gas for a given temperature. We also note that Boyle's law is valid for a hypothetically perfect gas without any restriction. Such a gas is called ideal gas. That is, Boyle's law is a fundamental relation between the pressure and the volume of an ideal gas. Inversely, we can also define ideal gas as the gas that obeys Boyle's law. The gas law allows us to introduce a concept called isotherm. The isotherms are functional relations between the pressure and the volume of an ideal gas at a constant temperature. That is, we can express pressure as a function of volume for a constant temperature. Or we can determine its inverse function, in which we express volume as a function of pressure for a constant temperature. Boyle's law expresses this relation between the pressure and volume as the equation of a hyperbola. Then the isotherms of the ideal gas are hyperbolas in the pressure-volume plot for given temperatures T1, T2 and so on, as shown in the plot. At a given temperature, the pressure of the gas is equal to the ratio of a constant divided by the volume of the gas. However, for each isotherm, that is for each hyperbola plotted for a given temperature, this constant is different. Let us consider now the isotherm compression of a given amount of ideal gas as an application of Boyle's law. In the isotherm compression, we reduce the volume of the gas and increase its pressure, while keeping its temperature constant. Describing the process in the terms of infinitesimal changes of these quantities, we can say that the change dP in the pressure of the gas is positive and the change dV in the volume of the gas is negative at a constant temperature T. Such a process can be performed in a cylinder with a moving piston compressing the gas in the cylinder, while we cool the system to keep it at a constant temperature. The initial state of the gas in the cylinder is the state A. Let the initial pressure and volume of the gas be P and V in this state. We can look up the constant temperature T from the pressure-volume plot for the initial values of pressure and volume. The final state after the compression of the gas is the state B. The pressure and the volume of the gas in the state B will be P plus dP and V plus dV, respectively. The volumetric difference dV is negative in the case of compression. During the isotherm compression, the gas changed its state from the initial state A to the final state B, moving along the isotherm of the temperature T in the pressure-volume plot, as we see in the figure. For such a process we can apply Boyle's law, which states that the product of the pressure and the volume of the ideal gas is the same in the initial state A and the final state B. That is, P times V is equal to P plus dP times V plus dV. The product in the right-hand side of this equation can be expanded as P times V plus P times dV, plus V times dP plus dV times dV. Here we neglect the last term, which is second order in the differentials of P and V, and keep the first three terms, which are equal to P times V in the left-hand side of this equation. Since the term P times V appears in both sides of the equation, it cancels out and we obtain that P times dV plus V times dP is equal to 0 in the first order. By dividing this equation with dP times P, we obtain a differential equation for the derivative of the volume with respect to the pressure. That is, the derivative of the volume V of the ideal gas with respect to the pressure P is equal to the negative ratio of the volume V to the pressure P. It is an important relation, which can be written in another form if we introduce isothermal compressibility denoted by kappa. Kappa is defined as the partial derivative of the volume V with respect to the pressure P at constant temperature divided by the volume V. The negative sign is for having a positive value for kappa since the derivative is negative as we increase the pressure. We see from the definition of kappa that the volume V times the isothermal compressibility kappa determines the tangent of the isotherm in each point. If we substitute Boyle's law into kappa defined by -1 over V times the derivative of V with respect to P, it can be written as minus the ratio of P to a constant C, times the derivative of the ratio of the constant C to P. This expression gives 1 over P. Then we see that the isothermal compressibility of the ideal gas is just inversely proportional to the pressure of the gas. For example, the kappa of the air is 1 atmosphere to -1, and this value is much greater than the isothermal compressibility of water, which is 5 times 10 to the -5 atmosphere to -1. Another application of Boyle's law is the derivation of the barometric formula, which describes the variation of atmospheric pressure with altitude. Since the atmosphere is an enormous volume of gas at rest under the influence of gravity, the pressure due to the weight of the gas decreases as we move from a given reference level to higher altitudes. Let this rectangle represent a portion of the atmosphere from the ground to its upper limit, where its density drops to zero. Its color gradient between blue and white indicates the decrease of pressure in the air column as we reach higher altitudes. For the sake of simplicity, we suppose that the air column has constant temperature. Here we consider two level surfaces represented with the green lines at an arbitrary altitude in this atmospheric column, where delta H denotes a small distance between the surfaces. Let P and P plus delta P be the pressure values at the upper and lower surfaces, respectively. The density in the thin layer between the surfaces can be regarded as constant. The pressure P at the upper surface of the layer is obviously smaller than the pressure P plus delta P at the lower one. The difference delta P in the pressure at the top and the bottom surfaces can be given by the formula describing the pressure at the bottom of a column of substance with a given height, which we obtained for Torricelli's experiment. Then delta P is equal to minus the density ρ, times the gravitational acceleration g, times the thickness delta H of the layer. The minus sign indicates that as the height h runs from a lower altitude to higher one, pressure decreases. Now we can divide the equation by delta H, while the distance between the two surfaces tends to zero. Then the left-hand side of the equation becomes the derivative of the pressure P with respect to the altitude h, which is equal to minus the density ρ of the air times the gravitational acceleration g, both measured at the altitude h. This differential equation describing the variation of pressure also holds for liquids, which are nearly incompressible and their density is constant. However, in the case of air, there is a functional relation between density and pressure, both depending on the altitude h. For the isothermal condition, we can use Boyle's law in the form which tells that the ratio of the pressure to the density is constant. We can choose the reference pressure P0 and the density ρ0 at the surface of the Earth. Then we write that the pressure P over the density ρ is equal to the reference pressure P0 over the reference density ρ0. Here we can express ρ as the ratio of ρ0 to P0 times P. If we substitute this expression into the differential equation, we obtain that the derivative of the pressure P with respect to the height h is equal to minus the reference pressure, times the gravitational acceleration g over the reference density ρ0, times the pressure P. Here the factor of the pressure P on the right-hand side is constant, and we can integrate this differential equation with the boundary condition, which tells that the pressure P is equal to the reference pressure P0 at the surface of the Earth, that is at h equal to 0. The solution is the barometric formula, which states that the pressure P of the air is equal to the reference pressure P0 times the exponential of minus a constant times the height h, where the constant is the ratio of the product of the reference density ρ0 and the gravitational acceleration g to the reference pressure P0. By using Boyle's law, we can write the barometric formula in the terms of density as well, where the density of the air is equal to the reference density times the same exponential term. Therefore the barometric formula tells that the pressure and the density are exponentially decreasing with respect to the altitude in a gas at constant temperature. This expression describes the distribution of the pressure and the density along different altitudes in the atmosphere for an idealized case, where the variation of the temperature is negligible throughout the air column. In the plot we can see the air pressure normalized with the reference pressure versus the altitude h measured in kilometers. The plot clearly shows the exponential decrease of the pressure as we elevate ourselves from the Earth's surface at sea level. We see that at the altitude of about 6 kilometers the pressure already drops to half of its value measured at sea level. When we exceed 20 kilometers in altitude, the pressure is only about 1/10 the atmospheric pressure at sea level. We can specify the reference values of the pressure and the density at sea level. The standard pressure P0 of air is equal to 101,325 pascals, whereas the standard density ρ0 of air is equal to 1.225 kg per cubic meter, both measured at 15 Celsius. Then we obtain 1.1186 times 10 to minus 4 meter to minus 1 for the factor of the altitude h in the exponent of the barometric formula. With these values inserted into the formula, we can calculate the air pressure at an arbitrary altitude. For example, since the elevation or the snow height of Mount Everest is 8,848.86 meters, the barometric formula gives the pressure of 35.4 kilopascals on the summit. This value is close to the average pressure measured there, which is 33.7 kilopascals. That is, Everest's summit has approximately 1/3 the air pressure that exists at sea level. We can demonstrate the variation of the pressure described by the barometric formula in a simple experiment with Ben's tube. This is a tube with two openings at its ends held in a horizontal position. If methane is pumped into the tube, then the gas escapes through the openings. We light the escaping methane after all air has been displaced from the tube, so that we could prevent the gas from burning inside the tube. We will see that the flames have the same size at both ends of the tube, indicating that the same amount of gas flows through both the openings. We can explain this result with the fact that the difference between the pressure of methane and the pressure of air is the same at both the openings. When the tube is tilted, the upper flame becomes larger than the lower one. This shows that the pressure difference between the outside air and the methane leaving the tube is greater at the upper opening than at the lower one. Since the density of methane is smaller than the density of air, the rate of the decrease in pressure of methane with the altitude is smaller than the rate of decrease for the air pressure. These rates are determined by the barometric formula, and this experiment demonstrates that the pressure must decrease more rapidly in the heavier air than in the lighter methane.